Hello everyone. In this lecture, I shall discuss the fixed point iteration method for solving the algebraic and transcendental equation. In fact, this fixed point iteration method is also called simply an iteration method. Now, coming to this method, we first discuss the definition of fixed point. What is a fixed point? Right, what is a fixed point? If a function phi is defined on a closed interval AB, and if it satisfies phi of alpha is equal to alpha, right, for all alpha in I, for all alpha in I, not for all alpha, for some alpha in I, for some alpha in I, some alpha in I, okay, then phi is said to have a fixed point, right? Phi is said to have a fixed point. That fixed point is alpha in I. That means if phi of alpha is equal to alpha for some alpha in I, then we say alpha is a fixed point in the interval I. For example, if we have a function, suppose we have a function phi x is equal to x square is my function. Now if I put x is equal to 1 here, then it is 1, phi 1 is 1. So 1 is a point here, right? So 1 is a fixed point here in this interval this. Similarly, that same function phi x is equal to x square, if I take a point 0 here, then what will find here? Here phi of 0 is equal to 0, is not it? Now likewise, if I take 2 points here, so here in fact you see both 0 is a point here and 1 is a point here. So now for both 0 and 1, we have phi of 0 is 0, phi of 1 is also 0. So 0 and 1 both are the fixed point of phi x is equal to x square in this, right? So this is all about the basics of the fixed point. Now this idea will be implemented in numerical methods, and this method is called the fixed point iteration method to solve the algebraic and transcendental equations. Okay. Now before the details of the discussion, let me to introduce myself, Professor Susanta Kumar Paikray, currently working as a professor in the Department of Mathematics, Veer Surendra University of Technology, Burla, Sambalpur, Odisha, India. So now, without much delay, let us have the details of our discussion. Geometrically, it is the point of intersection of, you see, let me to draw the graph first. The point of intersection of, suppose this is my xy plane here, right? So now suppose this is a curve, here. Now this is the line y is equal to x, right? Y is equal to x here. So this is my origin, this is the line, y is equal to x line. Now this point is my, suppose alpha 0 is my point here, okay, this alpha 0 is my point here. Now this point will be, this is y is equal to phi x, this line is my y is equal to, this curve is my y is equal to phi x curve. So now this is the point of intersection of this curve y is equal to phi x and y is equal to x. So at this point the coordinate of this point is alpha and alpha, okay. So this alpha is the fixed point here, okay. So it is the point of intersection of the line y is equal to x and the curve y is equal to phi x. So this is the geometrical interpretation of the fixed point. Now let us use this idea to implement for fixed point iteration method. Now coming to the fixed point iteration method, let you are given with a, let y is equal to fx be an equation given to us, right? So we rewrite this equation as, x is equal to phi x, okay. We just rewrite it as this, So now as per the definition, the root of y is equal to fx, the root of y is equal to fx, the root of y is equal to fx is the point of intersection of so let y fx is equal to 0 be a given curve. Okay, let fx is equal to 0 be a given curve, right? Be an equation given, right? Let it be my equation I, let it be my equation 2i. So this is the equation given I. We rewrite it in the form of 2. So the root of fx is equal to 0. The root of fx is equal to 0 is a point of intersection of here, as I have told you in the definition, y is equal to x and y is equal to x and y is equal to phi x. Okay, so let my initial approximation be, let x0 be an initial approximation to the root alpha in the interval AB, alpha in the interval AB. Okay, in this interval the root lies. So the first approximation will be x1 is equal to phi of x0, right? Phi of x0, and the second approximation will be x2 will be equal to phi of x1. If you go on continue here, xn plus 1 will be phi of xn, right? Phi of xn. So this is the n plus 1th approximation. Okay, this is the n plus 1th or general approximation. So this is the necessary formula, rather I can say this is the necessary formula, but subject to, right, subject to the convergence. Okay, I will tell you how it will converge. Okay, without this convergence condition, this root will scatter. So now, in order to understand this geometry of this method, we can understand it like this. So as per the definition of the fixed point iteration method, suppose you are given a curve here. So this is my x-axis and this is my y-axis. This is the curve given, y is equal to fx is a curve is given to you. This is my curve. So y is equal to phi x, as I have told you. Y is equal to, it is the point of intersection of y is equal to phi x and the line y is equal to x. So this is your y is equal to phi x. Now this is, suppose my line is y is equal to x is my line here. Okay, this line is my y is equal to x here. So now in fact this is my alpha here. Okay, so now this point is my alpha. This point is my alpha here. Right, this is the root, and we are considering x0 as an initial approximation here. Let my x0 is a point here. So my x0, let this x0 is a point here. Okay, so now this x0, I want to improve this x0. So I want to improve this x0. Let this x0 be improved to x1. Okay, let this x0 be improved to my x1. Okay, so x1, then this x1 need to be improved to some x2. Suppose some x2 is my here. Okay, some x2 is my here. Now. So now this x2 is again improved. Okay, again improved to some x3. In that way, will come closer to your alpha, right? In this way. Now this is the my fixed point here. Okay, so this is the point of intersection, and it is the point alpha here. Okay, the alpha is root. In this way, we go on approaching to alpha, right? So this is the geometry of the fixed point iteration method. So now what is the convergence conditions? Now whatever we write, not necessarily it will satisfy the convergence condition. So what is the convergence condition here? Now in short I am telling you the convergence condition. You see this formula here, xn plus 1 is your phi of xn. This formula, is it not same as this? Okay, so actually this is the formula and this formula is being considered out of this. Now the initial approximation lies in this interval AB. Okay, so the convergence condition here is, we write x is equal to phi x, that phi dash x modulus should be less than 1 when for all x lies in this interval, for all x lies in this interval AB where the initial root lies. Okay, so this is the convergence condition, right? This is the convergence condition here, convergence condition. Clear? So we write x is equal to phi x. There are different aspects of writing x is equal to phi x, but we choose that phi x such that your phi dash x less than 1. So for a given fx is equal to 0, we may have more than one such phi x, right? And we may have more than one formula here, right? And wherever the convergence is so slow, wherever the convergence is rapid. Okay, so once we take a proper approximation initially, then the convergence will rapid, right? But minimum this condition need to be ensured. Okay, so to understand this condition in details, let me to write. So what is the sufficient condition for convergence? The condition is sufficient only. Okay, that means you are given a function fx is equal to 0, let alpha be a root, right? This fx is written in this form, x is equal to phi x. Now this phi is a function from AB to AB is continuous, right? Is AB to AB is continuous. Now this AB contains your alpha, right? AB contains your alpha, right? Now if this condition holds, now this condition is called the Lipschitz condition. Lipschitz condition. If this condition holds, right, then we say that this iteration method will converge. This formula will converge to the root. Okay, now this formula is equivalent to this formula, right? If I bring back this to left hand side and take the limit here, right, equivalently this, then this lambda value is within 0 to 1, right? I am taking the mod here is less than 1, right? So here this x belongs to this AB. The interval may be open or the interval may be closed. Once this condition holds, okay, once this condition holds, then we say the sequence x0, x1, x2, so on, xn plus 1, right, defined recursively by xn plus 1 is equal to phi of xn, right? Xn plus 1 is equal to phi of xn, n is equal to here 0, 1, 2, so on, right? Converges to alpha for any x0 in AB and alpha in also AB. This root lies in this interval. Okay, so now the important thing is that the convergence of the function, the convergence of the now the given equation is fx is equal to 0. We create a formula, right? We create a formula. So what is the formula? We create the formula. The formula here is from this fx is equal to 0, we create x is equal to phi x. So this is the formula. Now this formula is rewritten as xn plus 1 is equal to phi xn. So to make it simple, let me to write the working rule. So coming to the working rule, consider the equation f of x is equal to 0. Let f of a into f of b is negative. So this implies root lies in between a and b, or in the interval AB. The interval may be open or closed. Okay, looking into this situation. The root lies between this. So the initial approximation, let x0 be the initial approximation. This x0 is a point, maybe here, maybe the end point, maybe any point in between, right? So now we rewrite it. So now the formula, okay, create the formula. So this is your intermediate value property here. Okay, now we get the initial approximation. Now we create the formula. Step 1, right? Step 1, rewrite fx is equal to 0 as x is equal to phi x, okay, such that phi dash x mod is less than 1 for all x in this interval, okay, for all x in this interval. The interval may be open or closed looking into the function is defined or not, okay. So now if this condition hold, then only your answer will converge. Clear? So this is the formula now this is my formula. So the necessary formula is thus the necessary formula is given by we write it here, xn plus 1 is equal to phi of xn. This is the formula, right? Here n is equal to 0, 1, 2, so on. Now here x0 is the initial approximation, right? Now putting n is equal to 0, your first approximation, no need to write step 1 here. Your first approximation will be for n is equal to 0, okay, for n is equal to 0, it will your x1 is equal to phi of x0. Then for second approximation for n is equal to 1, here x2 is equal to phi of x1, okay. We go on continue, n plus 1th approximation, or the general approx will be xn plus 1 is equal to phi of xn, okay, phi of xn, right? So now you go on continue, okay, such that, right, you go on continue x1, x2, x3, you go on continue, then you stop at a point where these answers are very, very close, okay. Suppose I am getting this answer as 2.578136, I am getting here it as suppose 2.578147. so now I am getting this accuracy up to 4 decimal places. So the up to the desired accuracy will continue, okay. So now coming to an example, use fixed point iteration method to find the root of this, okay. So here let f of x is equal to x cube plus x square minus 1, right? What is your f of 0? F of 0 is minus 1 negative. What is your f of 1? It is 1 plus 1 minus 1 plus 1 is positive, okay. As f0 into f1 is negative, so root lies in 0, 1, okay, root lies in 0, 1. So now we rewrite it, we create the formula, we try to create the formula, right? How to create the formula? So in one aspect, if I am going to write here x cube plus x square minus 1 is equal to 0. So what is my x cube here? X cube is 1 minus x square. So that means my x will be, or x square will be, if I divide one x here, it is 1 by x minus x. Then what is your x? X is my square root of 1 by x minus x. So this is my x. I may call it, suppose, my phi 1x. I may call it my phi 1x. In other aspect, I can see here, I want to create the formula in different way. Suppose I am creating here x cube is equal to, you see, here xq is equal to 1 minus x square. If I divide 1 x square, so what this implies, what is my x? Is 1 by x square minus 1. I call it suppose my phi 2x, right? And suppose in another way I just simplify it. I just simplify it in other way. Okay, here x cube plus x square minus 1 is equal to 0. Implies here x square into x plus 1, okay, is equal to here 1. Implies here x square is equal to 1 by 1 plus x. This implies x is equal to 1 by root over of x plus 1. Suppose this is my phi 3x. This is my phi 3x. Okay, this is my phi 3x. Now out of this, which one is the correct formula and which will lead you to the convergence? So let us now find the derivatives here. Right, if I find what is my derivative of phi 2 dash, phi 2x derivative, okay, so derivative of 1 by x square is minus 1 by x square is minus 2 by x cube, taking the mode here, okay. So here 0 less than x less than 1, right? So now this is not going to be less than 1. It is not going to be less than 1 for putting x in the interval 0 and 1, right? If I am taking x is 1 here, now it is 2. If I am taking x is 0.5 here, so it is more than 1. So this formula will not work here, okay. So this formula will not work here. So now you see here, if I am taking this formula, what is my phi 1 dash modulus, phi 1 dash x modulus, right? If I find the derivative here, so root over of x is 1 by 2 root x, 1 by 2 root over of 1 by x minus x. Again by chain rule, the derivative of this is minus 1 by x square minus 1, okay. If I simplify it, it will be my minus of 1 plus x square by 2x square into root over of 1 by x minus x, okay. So this is x, the modulus of this, okay. If I am taking x is equal to suppose 0.5 lies in this interval here, so this is my 1.25 divided by 2 into 0.25, here 0.5 into root over of it is 1 by 0.5, 2 minus 0.5, okay. So now you see, this is here greater than 1, this is here greater than 1, okay. So this formula will not work here. So this formula will also not work here. Now if you see the derivative of this, we'll find here, so you find the derivative, so this is phi 3 dash x, right? So x to the power minus half, so this is minus half root x plus 1 to the power minus 3 by 2 here. So you see, if I put x in 0 to 1, and definitely this mode is less than 1, okay. You put x is equal to 0.5, you see, and this mode is here less than 1, okay. For x belongs to your 0 1, right? X belongs to your 0 1. So now this is the correct formula. So therefore this is the correct formula. So thus the necessary formula is, right, in view of this is not according to the convergence conditions, and this will not converge, so we will consider this. Now the necessary formula is, right, thus the necessary formula is here xn plus 1, you see it, xn plus 1 is equal to 1 by xn plus 1 root over. So this is my formula, okay. This is my formula for n is equal to 0 1 2 with x0. We can take any value x0. I can take x0 any value, okay. I may take 0, I may take 1, or I may take in between 0 and 1 and value. With x0 is equal to 0 say, okay. So what is my for n is equal to 1, for n is equal to 0, what is my x1? It is 1 by root over of 0 plus 1 is here 1. Then for n is equal to 2, what is x2? N is equal to 1, here x2 will be If you simplify it, it will give you, just a second, 1 second. I may take any value. Suppose I am taking x0 is equal to 1. Okay. Let my, so it is my 1. So 1 by root 2. This is equal to my 0.70711. Now it is my 1 by here x1 plus 1 root over. Substituting x1 here and simplifying, I am getting 0.76537. Now you have to do one thing. You should store it in the memory of the, right? You should store, right? For easy calculation, store in calculator memory. Okay, calculator memory, and just go on replacing the value. Then your x3 will be, your x3 will be 1 by root over of x2 plus 1. If you simplify it, it will 0.75263. And similarly your x4 will be 0.75536, and your x5 will be 0.75477. Here x6 will be 0.7575496. Likewise, here x7 will be 0.75487. Now your x8 will be 0.75487. You see now at this stage these are correct up to 1 2 3 4 5 decimal places. Hence the root correct up to 5 decimal places is 0.75487, right? 487. So now in other way also, now the important thing is that how to create the formula, right? Newton-Raphson, in a remark I can say, your Newton-Raphson method, in a remark I can say Newton-Raphson method is also an iterative method. So in view of the Newton-Raphson method, we can generate a formula. That formula will also work for this method also. So in view of NR method, if I want to correlate it, in view of your NR method, right, xn plus 1 is xn minus fxn by f dash xn. So what is your fx here? Here fx is x cube plus x square minus 1. What is your f dash x? Is 3x square minus 2x, okay, plus 2x. So now, so this will be my, so this implies I can write it. So this is, I can write it x minus fx by f dash x to make it generalize. So this is x minus x cube plus x square minus 1 by 3x square plus 2x, okay. If I simplify it, it is 3x cube plus 2x square minus of x cube plus x square minus 1 divided by 3x square plus 2x, okay. So this is equal to here 2x cube plus x square plus 1 by 3x square plus 2x. So this can be taken as 1 pi x, okay. This can be taken as 1 pi x. So how to get it? You see now how to get it. So now this is pi x. So how to get it, this pi x, okay. You see, x cube plus x square minus 1 is equal to 0. So this implies your x cube plus x square is equal to 1. So this, if I add it, 3x square plus 3x cube plus 2x square here. So in this side I will add it. So I will add a 2x cube, I will add x square, right, and 1. Okay, now it is balanced now. So this implies if I take common x here, it is because in view of this I want to keep it in the denominator. It is 3x square plus 2x. It will be my 2x cube plus x square plus 1. So that means my, what is your x? X is 2x cube plus x square plus 1 by 3x square plus 2x. Now so this is my phi of x, okay. So this is my phi of x, right, in that way. So NR method is also a iterative method, right. So I have told you that how the convergence condition can be ensured in NR method, right. You can checking that phi dash x mod is less than 1 in this interval. You can check it also, right. So with this we can solve some more examples. In one transcendental example, let us solve now. Suppose you are given one more question. use iteration method to solve this. Okay, so coming to the solution, so my sin x is equal to 10x minus 10. So that means my 10x is equal to sin x plus 10. So what is your x? X is equal to, so x is equal to your sin x by 10 plus 1. So this is my phi xa. So this is my phi xa. So now what will happen to phi dash x? You check what is phi dash x. So derivative of sin x is cos x by 10. Okay, what is the my absolute value? So absolute value, cos x is less than 1, so it is here less than 1 by 10. 1, it is here less than 1 always, because the absolute value is 1 here, right? Since cos x is less than 1, right? So this is less than 1 by 10, so is it not less than 1? So the convergence condition is ensured now. So this formula is fine now. Now it will true for all x, is not it? It will true for all x, whatever x you take, this will hold. So for any x there is no restrictions. Okay, so we find the necessary formula here. The necessary formula here is xn plus 1. On this basis I write it. Xn plus 1 is my sin xn by 10. Okay, plus 1 here, right? So now for my what is my x1? N is equal to 0, 1, 2. So let I take my any value I can take. Let me take x0 is equal to 0 as initial approximation. So my initial x1 is equal to sin 0 by 10 plus 1. You keep your calculator in radian mode. You keep radian mode of your calculator. Okay, so then it will be, it is your 1. Then likewise you find x2. So x2 will be 1.08414, right? Here x3 will be 1.08839, and your x4 will be 1.08858. Here x5 will be 1.08859, and your x6 will be 1.08859. You see, you have to save it in the memory of the calculator, right? Before solving it, you save it in the memory of the calculator. How will save it? You just save it sin x 1 plus sin x by 10, sin x slash 10. Okay, in that way you just save in the memory of the calculator. Save it, right? You save it in the memory of the calculator. So now we see here the repetition is up to 1, 2, 3, 4, 5, up to 5 digit accuracy. These are same, in fact same. Hence this is my desired root. Now coming to one more example. So coming to the solution. So what is your fx? Fx is cos x minus 3x plus 1, right? So what is f of 0? Is 1 minus 0 plus 1 is 2, is positive. And what is your f of 2? F of pi by 2 you find. F of pi by 2 you find. It is cos pi by 2 is 0. It is minus 3 pi by 2 plus 1. Okay, and it is your negative. So the root lies between right 0 and pi by 2. 0 and pi by 2. Now what is my necessary formula? From this I have to create a formula here. So what is my necessary formula? Right, what is my necessary formula? So what is 3x? 3x is equal to 1 plus cos x. What is my x here? It is 1 plus cos x by 3. Let it be my phi x. So what is my phi dash x? If I find the derivative of cos x is minus sin x, right? So now if I take this modulus, right? If I take this modulus now, so now if you put any value here, if I put 0 here, sin 0 0, so it is 0. If I put 1 by pi by 2, then it is 1 by 3. It is less than 1 for x in 0 pi by 2. Okay, so this formula is a correct formula here. This formula is a correct formula here. So thus the necessary formula is xn plus 1 is equal to here 1 plus cos xn divided by 3, with I can choose any value x0. I can choose a value in this interval. So this is my formula. Here n is equal to 0, 1, 2. Okay, so this is the formula. Let my x0 is equal to 0. Any value I can take, 0, pi by 2 or anything in between this. Be the initial approximation. Okay, so now what is your x1? So x1 is equal to 1 by 3 1 plus cos 0. Okay, so this is equal to 0.6667. Then my x1 1 by 3 1 plus cos 0.6667. So this will be 0.5953. Likewise, if I continue, here x2 will be this is my x2. Here x3 will be 0.6093. Here x4 will be 0.6067, and here x5 will be 0.6072, and here x6 will be 0.6071. So if see up to third digit accuracy, right, it is third digit accuracy, it is same. Hence the root up to 3 decimal places is 0.607. Okay, so this is the answer. We leave it. Now coming to the summary of this discussion, this fixed point iteration method is one of the most efficient methods. Okay, now it is more efficient subject to the proper choice of phi x and your initial root x0, initial approximation. The convergence of this method may vary from 0 to n, right? So looking into the different choice of phi x, the convergence may vary, right? We can make the convergence not from 0, 1 to n, right? Now smaller the phi dash x, right? Smaller the phi dash x, more rapid is the convergence. And this method is useful in finding the real root. If a equation is having the complex root, this method will not that much useful. Now if we compare it, in bisectional method the rate of convergence is 1. It is linear. In regular falsi it is here 1. In second method it is 1.618 or here 1.62, and in NR method this is here 2, right? In case of simple root. In multiple root again it will linear, right? And in iteration method it may vary from 0 to n, right? So as per the proper choice of this phi x, if the convergence is n, then you see it is a more rapid convergence to get the answer quickly, right? So in fixed point method, we have to find the initial approximation by using intermediate value property. Then you choose phi x and satisfy that whether phi dash x mod less than 1 in that interval or not. Then only you can proceed. Otherwise, your answer will not fruitful. Once we get a root, suppose 5, again you may get 25, again you can get -1, right? Means it will diverge in that way. You will not get the convergence unless your phi dash x mod is less than 1, right? You cannot get a convergence proper root of these equations. Okay, so now with this my appeal to you, if I feel that this lecture is interesting to you, then please subscribe to this channel and like this channel, which will boost my motivation to create subsequent video for your benefits. Okay, so the lecture is getting lengthy. We should close it here. Thank you all. Have a nice day.